Okay, our next speaker is Justin Siegel, who is the director of IIFH, the Innovation Institute for Food Health, and the faculty here in chemistry, and one of our partners in crime here.
So this is great. Looking forward to the discussions today, and it's great to see everyone here discussing this topic. I always like to start meetings in the food system because with a slide such as this one, because the food system gets beaten and battered and demonized consistently. We always talk about all the problems in the food system, but I also think it's important always to take just a moment and appreciate how far the food system has come and the incredible advances that have happened over the 20th century. Over the last 100 years, at this point, we live in an age where it's groundbreaking news if 1,000 people got sick. 100 years ago, 1,000 people would die every single day of food poisoning. And now it's like, hey, this happened this decade, and that's a big deal, which is great. That's where we want to be, and that's happened because of food policy and all the technologies and innovations we just talked about that came with that policy. So it's not the #1 cause of death, food poisoning anymore. If you look at the science and technology in the food system, it's basically unparalleled, at least particularly the first half of the 20th century. There was a Nobel Prize practically every single year for the food system, learning about the essentials for human survival, whether it's vitamins, minerals, or essential amino acids, their structures, their mechanisms, their sourcing, their biology, just happened very consistently. And of course, the advances in distribution can't be overlooked as well. You can now go to Minnesota in January and find a fresh artichoke. My mother grew up in Minnesota and she had no idea artichokes came from the ground. She thought they came from cans. So the fact that, this is a picture I took in Minnesota in January. So it's stunning what's possible now. Next slide. That said, there's still lots of problems, and we talked about many of those this morning already, so I won't belabor it too much. We'll move through these, but this is one of my favorite figures because the first time I saw it, and I know many of you have seen it before, so I apologize, but it's just every time I look at it, it is stunning. This came from the New England Journal of Medicine, and it's basically showing that in 1990, you cannot find a single state with an average BMI of over 25. So as of 1990, you kind of in that 20-ish range is where your average BMI is, right? There's a big distribution in every state, but that's the average for each state. Today, you cannot find a single state under 25. There's been a complete shift in demographics in the population of the United States. And this is the exact problem that we were talking about just a few minutes ago. If you go to the next slide, this is not isolated to the United States. Oftentimes people talk about, oh, well, that's a problem of the fortunate and the wealthy in the land of abundance. That's absolutely not true. There was actually an article came out last year looking at globally the burden of obesity versus malnourishment versus hunger. And it's definitely true in 1990, if you look at this, you are not meant to be able to read all those little, but there's an article, the Lancet 16/2024, you'll be able to find this no problem. But there's 100 different, whether it's Thailand or Kenya or Italy or Greece or anywhere in the world, there's basically representatives of every single country in the world here. And uniformly, 1990, it's kind of you expect. There's a lot of places where obesity is an issue, but there's a lot of places where hunger is an issue as well. Today, uniformly, in every single country, that's the red lines in that circle there, as opposed to the light green lines, obesity is now the biggest global burden, more so than hunger. So if you want to improve the human condition, and I'm not saying we shouldn't fight hunger, to be really clear on this, hunger is bad, but if we want to fight, improve the human condition, it's about how do we think about optimizing, and no longer how do we deliver the minimum needed to survive, which is what we've done in an incredible way. But it's now how do we shift from what do we need to thrive? And the red lines are not thriving. Next line, next line. If you put this in economic dollars, this was a study done by the Rockefeller Foundation. In the United States, there's about $1 trillion, maybe 1.8 trillion, depends on the number you pick out, I guess, but it's a good amount of money. It's all still sub, like, I think maybe half of the NVIDIA total market cap, right? So we were talking about, it's like a $4 trillion market cap right now. So the food system's nothing relative to just NVIDIA, but that's why we're talking AI and the food system. And AI comes first, and the food system. So the current national expenditure in the United States is about $1 trillion, but the economic burden is about $3 trillion. So every dollar you spend is about a dollar that it costs you in health as well, and a dollar in environmental burden as well. So that $1 actually costs you $3 when you look at the overall impact on the human condition. Next slide. So, great, we're farther than we've ever been in the 20th century. We've done incredible, in policies and technology and science and distribution, logistics and everything in between, human knowledge and education. But obviously, there's still a long ways to go. It's far from perfect. And the opportunity here is now to use the current technologies to move things forward. And the AI and the food system can finally come together via cost curves such as this. The artificial intelligence over the last year has come to be and bear because of the changes in compute capacity. If you look at the last 10 years, based on Moore's law, the amount you can process per unit, roughly, there's been actually a 1,000-fold increase. Actually, it's moving faster than Moore's law at this point. We can argue if that's actually true or not, but that's what this graph says. If you look at analytical chemistry, and this one I will argue all the way, this is actually data from here at UC Davis at the Genome Center. I asked, hey, what is the cost to characterize a protein over the last few decades that you're charging people? And what we're seeing is about the cost to characterize a single protein through analytical chemistry, seeing the molecules of life, has decreased about 100-fold over the last 10 years. So the ability to characterize the compositions of the molecular basis of the foundation of what life is actually has decreased faster than Moore's law, which would be 10-fold over 10 years. And then, of course, genetics, our ability to read the foundation of life and manipulate that so we can produce the proteins or molecules or compounds we want, that's improved by about 20x over the last 10 years. All of these, the point is, exponential technologies, and they're not slowing down. They're moving faster and faster and faster. So if you want to catch a wave, it's at that interface of artificial intelligence and biology and food being at the center of it. Next slide. We've been doing this for a while now, for the last 10 years, and so all of these are different companies that I've had the privilege to help form and launch. And it's based on the problems that we just talked about and the technologies that we just talked about, and how we can bring those together to solve those problems. And if you go to the next slide, every single one of these technologies is based on understanding a key molecular component of the food. And pretty much all of these, actually yes, yeah, I didn't put the companies outside the food system in here. All of these are in the food system. And every single one of them comes down to understanding a molecule or a set of molecules at that molecular basis of things that we want in our food, or we don't want in our food, or we want to change how those molecules interact with our body. And as soon as we understand that molecular composition, because of artificial intelligence, analytical chemistry, genetic capabilities we have today, we can start building tools and systems such that we can address those problems or seize those opportunities. Next slide. The challenge is, I haven't started a company in like a year or two. It's because we're starting to run out, of the molecules we know in the food system. And I say that not lightly. It's not that we aren't characterizing the food system, but we've never really mapped the food system. Like when you look at papers and publications and what people are studying, it's the same compounds over and over and over and over again. If you talk about wine, people talk about resveratrol. For like decades, they talk about milk, they talk about whey and casein and lactoferrin. It's the same couple molecules over and over and over again, because that's where the light was shining. And that's what we could measure and we have measured for a long time. But I just showed you that we can now measure things at 100-fold cheaper than we've ever been able to measure. We have AIs and compute abilities to analyze data sets well beyond a couple molecules, well beyond what a human brain can comprehend. And we have the genetic tools to actually understand complete genetic compositions, molecular compositions of the foods that we're eating. And so for the first time in history, the tools exist such that we can do a complete molecular characterization of the food system. Next slide. And that's a program that we're starting. We work closely with IIFH, and we have some exciting news that I'm not going to disclose yet that's coming, but it's exciting news with this program. We're really starting to think about how do we work as a global consortium to do a full, in-depth molecular mapping of the food system, and not measuring a couple compounds with a standard USDA 100 compounds for each food, starting to map out on the order of 100,000 compounds in every food, and it's not just what's there, but the quantitative. How much is there across different processing methods, different origins, different agricultural practices, different regions in the world, like a really, really in-depth, 100x improvement in our understanding of the food system. Next slide. And I want to give you just a little vignette onto like what we're starting to do with this. So we've characterized about 1,000 foods so far, and we've characterized, I can't remember the number of molecules, it's at least 10 million compounds probably at this point it's at least 10 million. So we've quantified, at least semi-quantitatively, around 10 million compounds across 1,000 foods. And I'm just showing you proteins here, and I'm showing you this in a way that's structured such that across those 1,000 foods, we've quantified roughly 400,000 different proteins. And because we can quantify them and we know where they come from, we can start saying what's similar to what. And so what we're showing here is a cluster, and if two nodes are connected through an edge, so it's kind of compounds are clustered together, that means that there is a structural and sequence similarity between those proteins, meaning they likely have some relationship in terms of functionality. And whether that's texture or bioavailability or bioactivity, it's whatever that is there. 2 minutes left? All right, I'll just skip the last couple slides, which is fine. I had no idea how long we were going. And so what do you do with information like this? If you go to the next slide, well, you can do little simple things like this, where you can say, okay, if I have an egg yolk, what protein source has the closest proteins to it? And if you normalize that by abundance, molecular composition, if you want the closest functionality of an egg yolk, that protein is, you can now calculate to be a brown lentil. The proteins from brown lentils are the closest from egg to egg yolk. Ribeye steak, the closest is parsnip. I'm not sure you're going to be able to get enough protein from a parsnip. Just to be clear on that, I'm not advocating for that, but it's an interesting observation that you can think about. Milk, black beans are the closest, about 50% functional similarity. And this is just a little snippet. If you go to the next slide, you can think about allergenicity. Allergenicity, they're protein-based, which is the vast majority of allergenicity in the food system, is based on 8 amino acids, an epitope usually composed of 8 amino acids connected together to create an epitope that your body recognizes. They might be longer than 8, but 8 is usually the minimal viable unit for an epitope. And if you change the sequence of that epitope or change the abundance of that epitope, it'll shift how immunogenic that epitope is. And the further away in sequence and abundance, the less immunogenic it is. And so you can say, well, if you have a peanut allergy, if you think of every possible epitope in a peanut and you compare it to all those other foods, now that we have the quantified abundance of every one of those proteins, you start calculating the likelihood that you're allergic to or have an immune problem to other foods. So things like, well, it's not surprising if you're allergic to pecans, there's a high or allergic to peanuts, there's a high probability you have sensitivity to pecans. There's some actually sensitivity to soy milk. And if you're down at tofu, there's lower and lower, but there's a small probability. If you're sensitive to shrimp, again, it makes sense that high probability you're sensitive to lobster, lower probability to tilapia and cod, and practically nothing compared to turkey. So they're just showing you some basic things you can do, and again, these need to be improved using these systems. And then we'll skip to the very last slide. I was showing you a bunch of other stuff, but that can come later. It's all human health stuff. Keep going. We're going to go to the end. Thank you very much.
Okay.